All right, again, I'm trying to keep updated here with everything, and then I'll put a link. If you do need to go back a week, hit this bottom one, and then if it's highlighted, that'll take you a link directly to that day's notes, that day, whatever, for those. So, and then you can go back as far as needed to just see what's going on. All right, we will, like I said, talk about section 3.5, basic facts about complex zeros, conjugate pairs theorem, some good stuff. No guided notes today. No guided notes. Okay, we're going to factor and find all the roots for this one here, but let's do the law of signs, Descartes' rule of signs, to see how many positive and negative, just so that I feel more comfortable that you know it. So take a look at it. We'll take a look at the positive zeros. And we got everybody here. All right, hold on. And oh my goodness. Cool. He's still absent. Okay. All right. Don't graph it just yet on this one. Let's take a look here. All right. So for positive roots, you just take a look at the original function. And you see how many sign changes you have. Okay, going from positive term to a negative term. Well, x cubed is a positive term. Negative 5 is a negative term. That's 1. But negative 5 goes to positive 7, so that's 2. But that's it, right? So the number of positive zeros will be 2 or 0. Okay, to evaluate for the negative zero, now you got to plug in negative 8. What is the only terms that will change their sign for negative x? Okay, what are the only terms that will change their sign? Madison, let's see.
X to the third instead of an x.
Yep, if you have an odd power, even ones are just going to end up being squared back to a positive. Now, if you want to, put the negative x and do the whole thing, that's fine. If you want to just change the odd powers, whatever works for you, just don't get it wrong. Plus 7 times negative x plus 13. And so this will become negative x cubed. That will stay minus 5x squared. This will become minus 7x plus 13. All right, how many sign changes do I have there? Okay. Oops, that's a negative x. I just got 1, right? So 1, negative 0. All right, let's kind of go through our routine. What are our possible zeros? Hold on here. Move that down. Okay, this one isn't too bad because my A is just 1, right? So A is plus or minus 1. My B's, so I have 1. What's the only other one? 13. That's it. So my B over A is plus or minus 1, plus or minus 13. All right, go ahead and use negative 1 in your synthetic division. Okay, go ahead and use negative 1. We'll be using your calculators a little bit, so have them handy at some point here. think I'm talking about? Okay, so does -1 work? It's better. 1, -5, 7, 13, 0. 1 times -1 is -1, -6, 6, 13, -13, 0. All right, so we got f of x equals x plus 1 times x squared minus 6x plus 13. All right, now what do I do with x? Well, what I hope happens for x squared minus 6x plus 13. I hope it does what? Hope it factors. Okay, but this one doesn't. So if it doesn't factor, what do we have to do? Quadratic formula. Okay, so we got to do the quadratic formula here. And so in this case here, A is 1, B is -6, C is 13. So I get x equals 6 plus or minus. Oh, let me write down the formula just in case you need it. -b plus or minus square root b squared minus 4ac all over 2a. Positive 6 plus or minus -6 squared minus 4 times 1 times 13 over 2 times 1. All right, what do we end up with inside the radical? Okay, for that one. Tony, let me know what you get. Inside the radical.
Got -16.
Yeah, -16, that's what I got. All right, square root of -16, 4i. So what we got now is I got 6 plus or minus 4i over 2. And when you divide by 2, I get 3 plus or minus 2i. So my zeros are x equals -1, 3 plus 2i, and 3 minus 2i. Okay, 3 plus 2i and 3 minus 2i. All right, when you go to graph this, how many times will it hit the x-axis? Okay, how many times will it hit the x-axis? Cooper?
3.
Absolutely not.
Oh,
Are you kidding me?
Once, because those are irrational.
They're not irrational.
Oh, imaginary. No.
There we go. All right. If it's an I, 3 plus 2, that doesn't exist on the x-axis. That doesn't exist when we go to graph that. Okay? It's still a root. It's still, when you plug it in, gives you a 0, but it will not show up. Go ahead and graph it, just in case you don't believe me or Cooper. And then take a look at it. Now you can graph the original or you can graph the factored form. Where's my original? X cubed. Minus, if you got those newer ones that graph in color, it looks a little bit nicer. I need to upgrade. All right, so graph it. All right, it hits a -1 and then it disappears. All right, let's change your screen. See what else is going on in there. See if you can change anything else. Wow.
Yes,
So bad. All right, so I'm going to change my window. I don't even know what it's going to go up to, but I'm just going to change it to 30 and make that 3. All right, there, as you can see, there is a change of direction going on. I mean, that kind of indicates that there's complex roots. It's just not a linear equation that goes straight up. And it does have a local max and a local min, because if I kind of narrow into there, it was 3, 6, 9, 12. Let me just do something here. Just because I'm curious. 12 to 18. Let's see what that looks like. So there's definitely a change. So it goes up, comes back down. And since it's not on the x-axis, that kind of indicates, okay, we got some complex roots running around in the original graph. So if you graph it ahead of time, that kind of indicates that. All right, it says factored form. Depending upon the direction, there's kind of two ways you can go about this. First one will be right here, because sometimes it'll say factored into linear terms and any irreducible quadratic. So an irreducible quadratic is a quadratic that doesn't factor, because that doesn't factor anymore. But sometimes we want to take it down to all the linear terms, and what you can do is this is going to be x plus 1. Whatever root you have is x minus that root is the factor. So it's going to be x minus 3 plus 2i, and it's going to be x minus 3 minus 2i. Okay, and so you can take it down all the way to the imaginary or the irrational ones if needed. So you got to read the directions. Sometimes you say an irreducible quadratic, which would be the case where you get to this point, can't go any further with factoring. But if you want to take it all the way down to the linear terms, okay, that would also be the factored form. Okay. All right, factor and find all the roots for this one. I think we did this one Friday, but I can't remember. Josh is here this morning. Josh says, yeah. Go ahead and graph this on your calculator. Go ahead and graph, because that's kind of how we started here. I'm going to go through it quick. Go through it still. But if you got it down, just pay attention. I'd go back to Zoom 6 if you change your window. Okay. It hits at 2. It hits at 4. Pretty similar? Okay. Question is that a bend right there? Okay, and then how can we kind of test? Because when I first looked at it, I said, oh, it looks like you got a bend there. And a bend means what? If you got a bend there, at that point, what does that mean? It has a multiplicity of 3. So the question I'm saying, would this equation, if I say x plus 2 to the third power times, not x plus 2, x minus 2, and x minus 4, is that equivalent to that? Okay, how could you test it? Go ahead and graph it. Go ahead and graph it. I want you to see the difference. Like I said, you got those nice color ones. It's a little bit easier to see. But I'm going to graph. Clear this x to the 4th minus 8x to the 3rd plus 22x squared minus 28x, oops, plus 16. All right, there's your original graph. It goes through 2, it goes through 4, comes back up. It looks pretty much like there's something going on there. It's not the same continuous pattern the whole time. And so what I can do is I'm going to change my window a little bit. I don't need to go way to -10. I'm going to go to 6, and I'm going to change. I don't think I need to go to -10, do I? I can maybe get away with -6 to 6. Let's just see. All right, so you see that now x minus 2 cubed. x minus times x minus 4. So what's that look like? X minus 2 to the third power. And then x minus 4. All right, I think you can see when it has a bend, the bend occurs at the 0. There's a definite change as it goes through there, and then it alters. There's something going on in the other one, but it kind of occurs up above, and then it kind of goes back on its path. It's not great to see, but you can see it. Also, can anybody tell me there's another reason I know this one doesn't match up with that one? Anybody pick it, see why? What would be the constant term when I multiply this whole thing out? What would be my constant term?
32.
32, because this would be 2 cubed. It'd be negative 2 to the third power, which is negative 8 times negative 4. It would be plus 32, and that's plus 16. Okay, so that's another thing that says, all right, if I got a cubic there, it doesn't look like everything matches up. All right, go ahead and do synthetic division on 4. Do synthetic division with 2. Knock it all the way down, and then find your complex roots. You got 2 pieces. So I'm going to do, I know it's not going to be this. And I know 2 and 4 are my roots. So 2, I got 1, negative 8, 22, negative 28, and 16. Then that gives me 1, 2, negative 6, negative 20. 10 times 2 is 20, negative 8. All right, so you got to get a 0. We keep knocking it down a degree. And so now I got 4th degree, or 4 will go into here. 1, negative 6, 10, negative 8, 0, negative 2, negative 8, 2, 8, 0. So here, where are we at? We're at f of x equals x minus 2 times x minus 4 times x squared minus 2x plus 2. That would be factored form where you have an irreducible quadratic, because that third one there does not factor, right? So you could consider that in some form of a factored answer. Solving that for your roots. So x equals negative b plus or minus the square root b squared minus 4ac all over 2a. So that gives me, 2 plus or minus. Negative 2 squared is 4. Minus 2 times 1 times 2, right? Oh, I did something wrong.
Minus 4.
4 should be a 4ac. There we go. And then 2 times 1. And so that gives me 2 plus or minus, what is that, negative 4? Square root over 2. 2 plus or minus 2i over 2, which gives me 1 plus or minus i. All right, so now we got our zeros. 2, 4, and I'm just going to list this as 1 plus or minus I. So we have 4 zeros, factored form, final factored form with all the factors would be x minus 2, x minus 4, x minus 1 plus I, and x minus 1 minus I. Okay, so take that all the way down. If it depends on the wording of the directions, okay? But those would multiply back to get your original function at the top. So that's how we deal with complex roots. They won't show up in the graph, okay? But we got to be able to find them. All right, we've kind of talked about this, but let's kind of put this down as a fact. Complex and irrational roots always come in pairs. You cannot have one. And they come in pairs called conjugates, which means if you have 2 plus 3i, what also must be a root? Okay, 2 plus 3i, then conjugate is 2 minus 3i. Okay, always has to be in pairs. You do not have to have the real part. It could just be like a 4i. If you have 4i, you have to have minus 4i. Okay, that would be considered the same. And then same thing with irrational numbers. 1 plus square root of 7. You also have to have minus 1 minus square root of 7. And if you have like positive 3 square root of 2, you got to have negative 3 square root of 2 for that. All right, so always come in pairs. You cannot just have one. Okay. And that leads us to this. We can formally state this: a polynomial of degree n will have n roots, counting complex roots, anything with an I, and multiplicity. Okay, so a polynomial of degree n will have n roots. So if I got f of x equals 2x times x minus 3 to the 4th power times x plus 1 to the 2nd power, what's the overall degree of that? Overall degree of that is 7, right? So it has to have how many answers? It has to have 7. Now here's how you count multiplicity. Your zeros, x equals 0 would be 1, and that would be 4 of them. You would count, technically, 3 is a root 4 times. So that's how you count multiplicity, and negative 1 is a root twice. So you only have 1, 2, 3 distinct roots, but counting multiplicity, it has to add up to 7. Okay, for that one. All right, let's kind of put that together. Just look through this one, and then let's write the answer. I don't think you need to take the time to copy that whole thing down. Read through that. So polynomial of degree 9 with real coefficients has the following zeros: 2 of multiplicity 3, 4 plus 5i of multiplicity 2, and 3 minus 7i, right? All 9 zeros of p of x. So all I got to do is list the 9 zeros. Two of a multiplicity of 3. All you got to do is list that 3 times. Okay? So that's 3 of the 9. 4 plus 5, I have multiplicity 2. You got to list it twice. But since 4 plus 5i is a root, what else is a root? 4 minus 5i. And so it has to be a root twice. 4 minus 5i. 4 minus 5i. And then 3 minus 7i is a root, which means what else has to be a root? 3 plus 7i. They got 9 listed there? All right. So you got to have 9 counting complex numbers and multiplicity. All right, Cooper, back to you. How many times they going to hit the x-axis? Once. Good. It's going to hit it one time at 2. Now, it might have all kind of other crazy twists and turns in it, but it's only going to hit the x-axis one time. All right, let's take a look at this one here. This is one where we're going to have to write out the function, okay, based upon the information. Third degree, leading coefficients -4, and it has a zeros of 2 and 1 plus I. Well, if 1 plus I is a 0, what else is a 0? 1 minus I. All right, take a second here, think through what we're going to do. We'll grab. Jacob, what are we doing here?
So your roots are 2, 1 plus I, and 1 minus I. So you just have to do 3 things of x minus that. So x minus 2, x minus 1 plus I, and x minus 1 minus I.
Okay, good. So x minus 1 plus I, and then x minus 1 plus I. Don't let this -4 coefficient confuse you. All I'm going to do is I'm going to stick that out in the very front. Okay, and we'll deal with that later. One thing you can't do, though, is multiply those 3 together and just make your first term -4. That would actually change your roots. So now it's just in case we got to multiply through here, and at the very end, distribute your -4. Well, how do I multiply here? This is, I would distribute well, I made them both plus. Hold on. That should be a minus here, and that would make that a plus there. I always go back and forth here. The best way to multiply those together, I'm just going to take this x times, just multiply a trinomial times a trinomial. If you want to do what we did on Friday, make it a binomial times that, that's fine. But let's see here. If I take this x times all 3 of them, I get x squared minus x plus xi or ix. We'll go ix. And then -1 gives me -1x plus 1 minus I. And then the last one is a -I, which is -ix plus I, and then minus I squared. All right, just kind of something we're going to need here. Recall from before. What does I squared equal? Okay, I squared is equal to -1. Okay, so that will get replaced with a -1. Now, what happens to the other i's? Well, you got positive ix and a negative ix, and I got a -I and a positive I. So everything other than the I squared should cancel. I'm going to take 2 steps here. -x and -x is -2x plus 1 minus I squared. Well, what's minus I squared going to end up equaling? It's going to be minus a -1. So x squared minus 2x plus 1 minus -1. So in the end, I get x squared minus 2x plus 2. All right, those are those 2 multiplied together. I still have in front of it, what was it, an x minus 2? And I still have in front of that a -4. Okay, you got 2 options. You can either take the -4 times x minus 2, and then they take that thing times the trinomial, or multiply those 2 together and then multiply the whole thing by -4. It doesn't matter. I'm going to take the two polynomials and multiply them together and distribute the -4. Okay. All right, see what you get. See what you multiply x minus 2. If you're not sure, just wait. I'll do it here in a second. And I get, let's see here. X times x squared is x cubed minus 2x squared plus 2x minus 2x squared. Negative times a negative is a positive 4x minus 4. And that's going to give me x cubed minus 4x squared plus 6x minus 4. Okay. And so now, leading term is -4. Distribute -4 to everything. And so in the end, I'm going to have f of x equals -4x cubed plus 16x squared minus 24x plus 16. Okay, for that. All right, so in this section, complex roots, use your calculator to graph to find where the real zeros are, and then use synthetic division. So I'm not going to make you do guess and check on all of those. So that's 29 through 38 use your graphing calculator. To find the rational zeros. Okay, that's okay to do that.
What's that for? That ready? No, you think that.